Now let's move on. Now the first one, boron trifluoride, is rather easy. So now for the part A, okay, boron trifluoride. Of course, if you understand the theory, you need not to write any electron diagram. However, I will show you one by one because I find that still some of you don't understand about the molecular shape. Now, for part A, the boron trifluoride, if you draw the electron diagram, so boron will be group 3, so of course 3 electron in the outermost shell, and for fluorine will be 7. So I just neglect the lone pair of fluorine. So the electron diagram will be something like this. Now, how to change the electron diagram to the molecular shape? We simply count the number of sets of electrons here. Altogether 1, 2, and 3. So if 3 sets of electrons, okay, we should consider trigonal planar. And lone pair, so low lone pair of electrons. So we have the shape, okay, trigonal planar, and the name here. I want to mention, okay, some of you make some mistake. Someone write down boron, and then fluorine, and then dotted line fluorine. Okay, I'm sorry, it's wrong because it is trigonal planar. That means on the same plane. So if you really want to have 3D shape, you may adjust one with dotted line and one with pointing out the plane. If you really want to have 3-dimensional diagram. But I think it's rather difficult. If you understand what I mean, I think you better draw this diagram for boron trifluoride. Okay? So, the second, nitrogen trichloride, still many of you did not consider the lone pair electrons of nitrogen. That's why here I show you again, for electron diagram of nitrogen trichloride, there are 5 electrons for the nitrogen atom in the outermost shell. Okay, electron. Outermost shell 5 electrons. So in order to have electron diagram, so one sharing electron with one chlorine, one electron with one chlorine, and the other with one chlorine. So altogether, how many sets of electrons here? There are altogether 4. 1, 2, 3, and 4. Okay. So we consider tetrahedral shape because it is 4 sets of electrons. So if it is tetrahedral, we simply make nitrogen here and lone pair on top. 1 chlorine here, 1 chlorine pointing out, 1 chlorine pointing in. So the shape is not tetrahedral because lone pair will not count in shape. So the shape will be trigonal pyramidal here. Okay. So I will explain 2 more because the last one, sulfur hexafluoride, is exactly the same in your textbook. Okay, how about sulfur trioxide here? Okay, so some of you determine the shape, but the structure is wrong. Why? Because sulfur group 6, so altogether 6 electron. For oxygen will be group 6 again. Need to share 2 electrons, okay, for one oxygen. The other I won't show the lone pair. So altogether there will be 3 sets of electrons. 1, 2, 3. Although they are all double bonds. Okay. So what that means? That means if we draw 3 sets of electron will be trigonal planar. Yes, many of you write down trigonal planar. The shape is correct. However, the shape, the structure of the shape is wrong because it should be double bond, not single bond. Okay, so you need to use 2 straight lines rather than 1. Okay, this is for sulfur trioxide. So the other one, okay, for part D is a very, very difficult question. So I just simply let you know how to arrive this, and you may have make it as reference. I think DSE will not have this difficult question, but you know, for you, I try to test your ability on determining the shape. Okay, so how about for this one? If you draw the electron diagram, I put it here. Chlorine will be 7 electron. So If it want to bond with a fluorine atom, there will be 3 covalent bond formation because for fluorine is group 7 also, share 1 electron. So for this electron diagram, you can count 5 sets of electrons, 2 lone pair and 3 bond pair. So if 5 pairs or 5 sets of electrons, we should use trigonal bipyramidal. However, some of you simply write down chlorine and then upper part and lower part with lone pair and 3 fluorine molecule exactly like this one. And you mentioned trigonal planar. So in fact, in the lesson, I try to explain this molecular shape. It is wrong for trigonal planar. Why? Although the lone pairs with 180 degrees, okay, the largest angle so that they can separate to minimize the repulsion. However, the lone pair and bond pair only 90 degrees. Okay, and although bond pair with 120 degree. Okay, but it is not the most stable one. Why? Because the lone pair bond pair here with a smaller angle compared with the bond pair angle. You know, according to valence shell electron pair repulsion theory, that theory indicates the shape of molecule governs the repulsion between the electron bond pairs. Right? Lone pair bond pair must be larger than lone pair bond pair, must larger than bond pair. That's why we have this shape. This shape, the lone pair I won't show here. The lone pair should be in the plane and out the plane. Okay, and you find that this lone pair will be 120 and lone pair bond pair will be 120, more or less the same. And also bond pair here will be 90 degrees. Okay, what that means? That means it obeys the valence shell electron pair repulsion theory, and we name this kind of shape as T shape. But I find that I forgot 1 or 2 of you can answer correctly about the shape. Maybe from outside tutorial. Okay. So I think that's all for molecular shape. Okay, please, you need to understand what I'm talking about. Okay. Now we move on to question number 2. It's about the definition of 2 words. Okay, one is the electronegativity. Is rather easy. You can simply make it or find it from your textbook. It's the ability to attract the bonding pair electron within a covalent bond. In fact, some of you simply write down the ability to attract electrons. However, for electronegativity, we focus on the attracting ability on bond pair electrons, so that there will be some polarity between a covalent bond. So for number 2 is about what is means by polar covalent bond. In fact, it's a covalent bond, okay, with atoms of different electronegative values. One with higher value will attract the electron, so that there will be partial negative charge on that atom. Okay, that's why we have, for example, hydrogen chloride. Okay, the chlorine with higher electronegative atom will be partial negative, and for hydrogen will be partial positive. So there will be a polar covalent bond here. Okay, with our polarity. So for part B, rather easy, but still some of you mess it up. You try to give an example with polar covalent bond and the other without polar covalent bond. So how to make it? As I mentioned, okay, HCl will be with polar covalent bond because there will be difference in electronegativities, okay, between the atoms. So how to cope with one molecule without polar covalent? Quite simple. You simply use an example here, for example, chlorine, because both atoms with same electronegativity values. So no difference in electronegativity, that means no polarity here. But someone mentioned boron trifluoride. However, boron trifluoride is wrong here, because boron trifluoride, okay, here, although all dipole moments are balanced, but still there is polar covalent bond here. Okay, you need to mention one molecule without polar covalent bond, but not without net dipole moments. Okay, that means some of you still mess up about the terms. Okay, now part C. Again, I just use the classwork example. Okay, last time I mentioned I used Stephen Charles wordings. Okay, so is it possible to have a polar covalent bond but the molecule is non-polar? Okay, so there will be possibility. So the sentence will be no, because for polar covalent bonds in opposite direction, there will be non-polar molecules. Some of you have detailed explanation like the dipole moments of the polar covalent bonds all cancel each other. The molecule is symmetrical, so it will be non-polar. Of course, much better than my explanation because I just simply use 2 marks here. I need you to answer yes or no. That means you agree or disagree about the statement. And 1 mark for explanation. And 1 mark, I want you to show one example that you can explain why there is polar covalent bond but the molecule is non-polar. For example here,